excited to introduce you to this panel. We are talking about electric plane and the innovations in electric plane, how it is being used for training, pilot training, what type of infrastructure we need to accommodate electric planes, eVTOL, and the future technologies that are coming up from electric planes. So I'm very excited to hear more from all the panelists that we got here. We got panelists from CAE, from Beta Technologies, Harbour Air, WWFC, University of Waterloo, and also Pipstroll. So very exciting panel. And first, we're going to start with my co-chair here, J.R. Hammond. Thank you, Jay.
So bonjour tout le monde. Good afternoon, everyone. Grateful to be back here in Waterloo for the third Sustainable Summit hosted by WISA. As shared by my co-chair here, Merta, this is our third time being here present as not only a member of the WISA Advisory Committee, but also supporting the great work that Dr. Suzanne Kearns has launched here in Waterloo and making sure that's translated across the country. So I'm going to be brief in our introduction because we will give the majority of the conversation to our experts here in the panel, but we wanted to make sure we could set the stage of why this work is important across the nation of Canada and how it's expanding on the international side. So as an overview, my name is J.R. Hammond. I'm privileged to serve as the Executive Director of Canadian Advanced Air Mobility, or CAM for short, and we are the Federal Industry Association responsible for enacting and operationalizing advanced air mobility in the country of Canada. We operate across the country, and our main focus is to really take what is this advanced air mobility and turn it into operations for us here in Canada. The critical piece, though, just to set the framework on where our conversation will be expanding today, is what is this definition? For us in Canada, we focus on three main pillars. Primarily, the new propulsion systems that are going to be entering our aviation industry from both electric, hydrogen, and further new propulsion technologies. Those new aircraft architecture that take our existing understanding of conventional takeoff and landing aircraft, our fixed wing, the vertical takeoff and landing aircraft, and of course some of the blended wing bodies that we're seeing in some of the future commercial designs as well. And that third piece, when we combine these together, what unlocks the new operating and use cases across our country? How are we moving people, goods, and services in unique ways that aviation wasn't feasible or economic in the past with conventional technologies? So for us, we really want to make sure that in Canada, the AAM framework extends to this evolving aviation ecosystem. And these are some of the images which our incredible panelists will be speaking about in their area of expertise. But the advanced air mobility narrative starts with all of the great work coming out of the RPAS industry, the remotely piloted aircraft systems, on some of those autonomy pieces, as seen here by the Indro Robotics Wayfinder, that's been operating commercially in Canada since 2016. That then unlocks all of the work that Blago will speak about from Harbour Air on the retrofitting of existing aircraft and showcasing this new market operating opportunity across our country. We'll then have the incredible Madison give some of the insight of the electric trainer aircraft, as well as our Waterloo friends, showcasing not only commercial operating opportunities, but what this means for our new pipeline of talent for pilots needed in the future, and of course the existing aviation industry. And then we'll have Sky speak more about from Beta, how our new aircraft architecture will have a space in moving cargo, people, and some of our emergency use cases, with the entry into service being our launch customer with Helijet in British Columbia and Beta Technologies for our 2028 timeframe. And then all those pieces help us unlock some of the more future opportunities that we're making sure are a part of the AAM ecosystem, this here being one of the examples of the Boeing-backed Wisk Gen 6 aircraft that is a fully autonomous electric vertical takeoff and landing aircraft that we're guesstimating at about a 2030 plus time frame for opportunities and operations in the Canadian context. And of course, it would be without importance if we did not include our conventional aerospace and aviation partners to make sure that all of this work transitions into our commercial aerospace sector as well. And all of these together under the AAM framework give us an opportunity to engage and ensure each one of these pillars plays an important role in that evolving aviation ecosystem across the country. And so as the industry association, working with our partners here and our incredible panelists, we have a mission to make sure we enact operations for advanced air mobility well by that time frame of 2028 for initial entry to service. And this cannot be done in silo. Our last and most critical point is showcasing how it's all of our international, federal, provincial, and of course more recently our municipal aviation partners that need to play a role in both the sustainability side and, as Dr. Kearns gave allusion to this morning, those environmental, economic, and social pillars that will help unlock the future of this technology within our country's operations. And to conclude with, we cannot give enough importance to the existing regulators that are helping on this cause. Transport Canada, as our civil aviation authority, as well as NAV Canada, our air navigation service provider, have been sitting with us on a quarter-by-quarter basis to help chart out the challenges, the hurdles, and the near-term opportunities for these projects at hand. They are the ones that will continue to champion with this advanced air mobility integration team and will further help us unlock these new technologies that our panelists will speak about. So we'll leave here on just a thank you for welcoming us and being a part of the conversation today. We have a lot of work ahead still for the country of Canada and to take a leadership role on the global stage, but we're going to pass it on to our first speaker, Richard from CAE, to give some of the insight of the work going on the CAE side. So thank you so much.
Okay, well, the slides are coming up. Hello, everybody. Thanks for coming to watch this and hopefully learn a little bit about our program and the other ones that JR has just been through. Almost had it. There we go. So maybe I'll just start with introducing myself. I'm Richard Alexander. I'm an aircraft integrator with CAE, working on our electric aircraft program, where we're converting our Piper Archer from avgas reciprocating engine to electric. So CAE are known for our training, our simulators, our digital products that support all of aviation. So what are we actually doing? Why are we doing it? Where are we up to? And a couple of the challenges that we're facing along the way, I'll mention in this presentation. So I guess I'm in control of this, aren't I? Okay, so when I first joined this project, I was a little bit surprised that CAE operates a fleet of over 200 single-engine piston aircraft in a flight training environment. So we have Piper Archers, we have Diamond 40s, we have Cessna 172s and others. You can see them on the right-hand side there. And if you look at the bottom, you can see the type of carbon emissions that those operations generate throughout the world. We're a global training operator. You can see that we generate about 20,000 tons of CO2, of which about 13 or 14,000 is from our flight training operations. So there's an opportunity there as a company to reduce that by electrifying our fleet. So that's what we've chosen to do. A little bit about our training organization and what the needs are. So we know there's a few challenges. So there's a few needs that come from our training organization. The first of which is the flight duration, which I'll come back to a little later. So we want to be able to fly a training mission for at least an hour with 30 minutes reserves, preferably an hour and a half, which covers most of the work that happens near to the airfield. The bottom right-hand corner, you can see the graph there of a few aeroplanes over a couple of days. You can see where they go from our training school in Mesa, Arizona. So they fly, let's call it 25 nautical miles. So maybe it's 15, 20, 25 minutes away from the airfield. So we're not going very far to conduct these operations. It's very important that we're in a commercial competition with other service providers. You can see some of the airlines that we train their pilots on the top right hand there. They're typically big airlines, so it's important that whatever we do with electrifying this training fleet is that it doesn't take us any longer to train any individual pilot, which given the flight endurance is a bit of a challenge because it's going to take us multiple flights to impart the same training on a candidate that normally would be done in 1 or 2 flights. So those customers that we have, and it was interesting in the the main presentation this morning is that Southwest were identified as an airline that have lots of sustainability thoughts in the way that they operate. They're one of our customers. But we have to get all of those airline customers to buy into what we're doing with electrification and including it in their very well-regimented curriculum that they have for pilot training. So it has to fit, basically. Also, it's not a gimme. You can't go and find a mechanic that knows how to operate or maintain electric aircraft. They don't grow on trees. There's not many of them around. So there's a lot of logistics and infrastructure that we need to put in place to also support that training operation with electric aircraft when it comes in. And here at Waterloo, I know you've been through some of those thoughts as well. It's not a straightforward activity. We need chargers, we need people that are qualified, we need the space, we need the grid system to support it. There's a lot of thought needed. So there's some of the things that our training organisation needs to be able to incorporate the electric aircraft in their training plans. Okay. So this is just a little overview on who's helping us and what are we actually doing. As I mentioned, CAE doesn't make aircraft. That's not our business. So we've brought in a number of experienced companies that have done this before. They supply the right stuff, and they're helping us put together this integrated aircraft that we're going to put in service. So we have Ellison, who are a Montreal engineering company, and so their design approval organisation is how we'll certify the aircraft, and they're also helping us with design work. We have Piper. It's very important to have the original equipment manufacturer on board. They're giving us access to all of their dusty archives and all of the old data that we need to support this STC that we're going to do on the aircraft. Safran are making the electric engine. Cert Centre Canada are going to be conducting our flight test program from Saint-Hubert near Montreal. They also provide the flight analysis and human factors aspects of the program. H55 are a battery company that are based in Sion in Switzerland. They're the ones that are going to be providing our battery packs. And they also have just opened a facility again in Saint-Hubert on the south shore of Montreal. So they've moved into the country. So they're our battery supplier. And we also have a few academic and research partners, primarily University of Sherbrooke, and we've done some work with NRC, so the National Research Council of Canada. And as you can see at the bottom there, we want lots of nice, happy, trained student pilots at the end of all of this. That's the goal. So everything that we do from the design aspect, our requirements are all driven by what we need those student pilots to be able to do in the end. What we're actually doing with the aircraft, so we're removing the reciprocating engine, the fuel system, the propeller, the aft seats. It was a four-person aircraft, now it's going to be 2 occupants. We're going to add the electric engine, lithium-ion battery system, and a new propeller. And one of our golden rules is that the PA-28 family first flew in 1960. If it works, don't touch it. So there's much on the airplane that we can improve things if we want to. We can make it a nicer experience for the training mission. But hey, we're not touching it if it already works. If we don't have to. So that's one of our golden rules also. And you can see from the picture at the bottom right where we put the batteries on the aircraft, which is probably the biggest integration issue because these things are heavy, they take up quite a lot of volume. We've basically put them where there was mass before. That's essentially been our approach. So we have battery packs in either wing where the fuel tanks used to be. We have them behind the engine, in the engine bay, where a really heavy engine used to be. And we have them where the aft passengers would sit, so the back 2 seats. That's why we're only 2 people now, because it's full of batteries where the other 2 would have sat. Okay, just an overview of the timeline. The program was launched at Farnborough in 2022, and we've been following a pretty standard engineering process. We played around with configurations. We had a preliminary design review earlier this year that enabled us to go into detailed design. So we're now actually drawing things to actually go and make parts on the aircraft. And then we'll be building the test vehicle and flying it next year from Saint-Hubert or Montreal Metropolitan Airport now. It's gone up in the branding stakes. Transport Canada and FAA will hopefully be certifying the aircraft in the 2027 timeframe, after which we'll go and enter into service. And most of these, if not all of these aircraft, will be in Mesa, Arizona, our training school there, which brings in another challenge. It's really hot most of the year there. Batteries don't like hot, so another challenge. There's three challenges I've put here that as an engineering activity that we've got to overcome. They're very common. You've probably heard about them before if you follow electric aircraft. For those of you with sharp vision, you could see that yes, there is an elephant in the room there behind. But by the time the energy gets from the energy system, whether it's fuel or battery to the propeller, avgas engines give us like 14 times as much energy at the propeller compared to batteries. So that's a big one to overcome. On the right-hand side there, you can see for the same mass of our current fuel system and avgas, that aircraft can fly for over 4 hours. When we put the same weight of batteries in there, it can fly for about 20 minutes. So that's quite a problem to overcome. So that's one of our challenges. We're happily fighting the laws of physics and having some negotiations. I wouldn't say we're winning all of them, but we're getting there. Aircraft certification, I think has been mentioned before. On the right-hand side there, you see all of the different parties that are involved. We're trying to come up with a set of rules for certifying these aircraft that are trying to grapple with the fact that most of the legacy rules are built around air-breathing engines. The electric motor, it doesn't do that. The batteries, they don't do that. So a lot of the rules are not directly applicable in standards. So we're working together as one big happy family to try and make a sensible set of standards for this kind of aircraft that we can certify and put in service. And I mentioned goalposts at the bottom there. On a daily basis, we're converging, but we're making a design based on a set of assumptions on what we have to do to certify, and it's going to change before we actually certify, so that's a continuing challenge. And then finally, mentioned in the 3-minute thesis this morning is the problem of battery thermal runaway, which is a state where a mechanical impact or what have you, a nail is a popular one going through a battery, or a quality escape in the batteries can lead to a condition called thermal runaway. And it is quite spectacular, and you can see in the top there, a single cell we have 4,800 on the aircraft. So if a single cell goes into this state, it can spread to the or propagate to the batteries around it, and that's obviously not a good thing. So what we have to bear in mind when we're actually designing the aircraft is that you can either choose to try and fully contain it within the box that the batteries are in. You have to, vent the batteries and anything that comes out of those cells overboard so that you don't just build a massive gas box, which then you don't know what to do with. And also you have to decide how much am I actually going to try and protect from this case by not allowing it to propagate to the cells next to it if one battery goes. So there's some material such as phase change material, whose job it is to actually absorb the energy that would come out of a battery going into thermal runaway so that it doesn't spread to the one next door. So these kind of things have to be considered, and how much you want to do on stopping it from propagating or stopping it from happening versus containing it within the box that they all live in. And then finally, whatever you do, to convince your authorities, we're going to have to test. And you can see the bottom picture there is actually one of our wings that was used for a thermal runaway test, to better understand actually what happens within that cavity when a thermal runaway does happen. So that's just an example of the type of experimentation and research we've been doing. That is it. Did I make 10 minutes?
Exactly.
Good afternoon. Thanks so much for the participants and organizers for letting us be here. It's a really exciting event, so thank you so much. What are we doing at Beta? We're building electric aircraft. But we're doing a little bit more than just building electric aircraft. And I'll touch on some of the other aspects that I think are what is needed to really make this technology a reality. So we're based in Burlington, Vermont. We have been around for a few years there, and we're approaching about 800 employees, so we've experienced pretty rapid growth, and we are privately held. So, as I mentioned, we're not just building electric aircraft to deliver to our customers to allow them to complete their missions. We're creating an ecosystem, again, to really allow our customers to fully realize this technology. We see it as aircraft, of course, being a major component of that. That's a headline, rightfully so. It's where the bulk of our resources are leveraged. But the training side of things, as is a key focus at this event, as well as the infrastructure component, are major things that need to be addressed as well, again, to really move this into commercialization. Before I go too deeper into any of those aspects, these are some of the folks from the financial side of things, as well as the operations and other aspects, and our government partners who have trusted us with their resources, time, and commitment. We are very proud, again, to mention our Canadian VTOL customer, Helijet, which we look to deploy to in the next couple of years. Two different aircraft. One on the left, our CTOL aircraft, conventional takeoff and landing electric airplane, utilizing existing infrastructure, runway to runway, certified Part 23. And then the aircraft on the right, which is under the powered lift category, 2117B, again, able to utilize existing infrastructure as well as runway independence as well. This is a timeline for our certification goals. On the left, you'll see our motor, which is going to be our first certified product. We will then move into our CTOL aircraft, which will be certified later next year, and then finally into our VTOL powered lift aircraft, certified the following year. We try to really let our work kind of speak for itself in regards to what we're doing in the space. That being said, there are several milestones that we're very proud of. Most notably, without reading through this entire list, I'll point to a couple, specifically the quality valve flights with the FAA, U.S. Air Force, and Army. Those are the first that we're aware of in its kind in this space, and we're again happy to share those learnings with those government authorities and partners. I'll talk a little bit about charging here momentarily, but we feel that it's really important to avoid some of the confusion and missteps that the automotive industry has experienced as it relates to standardization and charging infrastructure. We have done that by reaching out to the partners in this space, our competitors, our partners, our customers, and others, to really understand what a common approach could be to this. And we have a couple solutions that we've deployed at multiple airports in the US and soon to be Canada and elsewhere. We are deploying this on airport primarily right now, and that is our charge cube that you see in the larger picture there, utilizing the CCS standard, which enables our aircraft to charge in just under an hour from reserves up to a full charge. It's also multimodal, meaning that it can charge GSE and other ground-based equipment as well. So it's not just our aircraft and other OEMs aircraft in space, but also, again, belt loaders, tugs, airport operations vehicles, and the like. This is a little dated. We're actually over 40 sites online now, mostly on the East Coast and down into the southeast of the US, as well as on the West Coast in California, again, moving into Canada shortly. We've taken some pretty big strides as it relates to our aircraft certification, as I mentioned, but also on the build out and the industrialization of our facility as well. Our final assembly facility is online and active today, and we just recently, as of last week, flew our first aircraft that came off of that final assembly line. That is just the beginning of our production, and we're looking forward to delivering multiple aircraft off of that line in the weeks and months to come, again to our customers in the US as well as north of the border here in Canada. Thank you so much.
Can everyone at the back hear me okay? Thumbs up in the back, yeah, good. All right. Good afternoon, my name is Blago. I work at Harbour Air. Thank you, WISA, for inviting us to participate in today's panel, which I have to say is a pretty excellent panel considering the diversity of approaches that are being taken to make electric aircraft feasible and operationally successful. Harbour Air's approach started with this man. He's our co-founder, Greg McDougall. He started the airline in 1982, and he said, if we sit here looking out the window, one of these days something's going to be flying that's going to rock your world, and I want to be the one flying it, not the one watching it. So that inspired the team in 2019 to take our baseline de Havilland Beaver aircraft that we run in our fleet. It's up gross to 5,600 pound maximum takeoff weight, and we removed the entire power plant, the piston, engine, the fuel tanks, the 3-blade prop on there, the entire cabin, and we installed an entire all-electric powertrain. And that was eBeaver 1.0. That aircraft flew on December 10th, 2019. It was the first all-electric seaplane flight in the history of aviation. So it was a big day for Harbour Air and for the aviation community. And it only flew for a few minutes, but there were some interesting things about that airplane. It contained an electric powertrain, as I mentioned. It had a Magni 500 motor in it, derated to 450 horsepower, which is the same takeoff power as the baseline aircraft. It had 4 inverters powering that motor, and those motors drew energy from 3 battery strings of lithium-ion batteries, all bussed together for a total capacity of 143 kilowatt hours, so roughly 2 Model 3s worth of batteries. We also had a 4-bladed propeller on there. It was a brand new propeller from Hartzell, also experimental. And that aircraft has undergone many hours of ground testing. It's completed 78 test flights, and we learned a lot. We learned that the performance of the aircraft improved in a number of ways. That propeller I was mentioned is a very good propeller for producing thrust compared to the baseline aircraft. We had about 25% more thrust with that prop. And then you can also see that the nose is a lot more aerodynamic than the baseline piston beaver. So what that resulted in is a reduction in our power required for level flight from 62% on the baseline aircraft to 41% for the eBeaver, and same maximum takeoff power. So we had a massive reduction in the cruise power required, and what that allowed us to do was fly a lot longer than was originally anticipated. And that right there is probably the single most important point as to why the Beaver is going to make it for operational electric aircraft. Secondly, due to the aerodynamic improvements, we also had increased takeoff performance and climb performance. And we also learned a lot that probably the number one challenge, and I think you'll hear it today in discussions with batteries, is thermal management. When we were flying this aircraft, we would heat those batteries up 25 to 30 degrees Celsius in one flight. And then we have to wait for the aircraft to cool down before we could charge it again. And we charge the aircraft, also increase the batteries by another 20 degrees, have to wait for it to cool down. So we had pretty extended times between our ops, and that was not going to work when it comes to an operational sense. The other aspect that was challenging with this battery system was keeping the batteries in a consistent temperature range to the point where you need them all within 15 degrees Celsius, and we exceeded that delta at some times, was challenging, especially during outdoor charging activities. We couldn't actually charge the aircraft at some times because the temperature delta was too great on the batteries. Speaking of charging, charging is only as good as the power you have available to you, and it's only as good as the cleanliness of the power you have available to you. So in our hangar, we have a 60 kilowatt fast charger. We can charge the aircraft in about 2 hours. But when we flew the aircraft on its first point-to-point flights to some of our more remote bases, we had to sit and charge the aircraft for 15 or 16 hours with a 7 kilowatt charger. So not ideal from an operational standpoint. So these are all big challenges that need to be addressed if we're going to make this successful. Now, all that charging, temperature regulation, the batteries that we used, they were a Gen 1 battery system from our supplier, EP Systems. And those batteries, they degraded over 3.5 years. And we have actually had to replace the entire battery system on the aircraft last year, which we completed earlier this year. And we call this eBeaver 1.5. So this has a brand new battery system in it. It's got a Gen 5 battery system. And we call this our 1.5 because it's like our halfway point between our prototype and the certification version of the aircraft. So what changed? Well, we increased the voltage from 500 to 800 volts. That's our max voltage. And we introduced another string of batteries. So previously on the electric aircraft, we had those 3 strings all bussed together. On this one, we have 4 strings of batteries, each independently powering 1 inverter. We also increased the capacity by about 10%, so we get 10% longer flights. The thermal runway containment strategy was a lot different. So the battery modules, which you can see in the bottom corner there, they're actually designed to contain an entire thermal runway inside the battery and then vent it out a dedicated port. So we had to design the venting system and integrate that into the aircraft. Whereas the previous modules were designed to prevent propagation between the cells. That resulted in a much heavier module, but this one has a lot more energy behind the failure, and you have to account for that. So this actually took us a while to figure out a good solution, and ultimately we have a pretty heavy solution right now, so there's areas for improvement here. We did a software update on the inverters, and we also updated the engine and ESS display. And you can actually see in the bottom picture, there's two displays, one on the center pedestal, that's the engine display, and the one on the right is the ESS display. And when I say engine, you're wondering what the heck is an electric engine? Because we have electric motors. Well, I didn't write the rules, but we're certifying it as, or the engines or the electric motors are being certified as electric engines because that's the way the rules are written. So we've done 18 flights now with eBeaver 1.5. We're getting close to our 100th flight with the aircraft, which we're going to do something special for. And so far we have a much simpler charging process, and we have much better thermal performance with these batteries. We don't have near the temperature rise during our flights, nor our charging, so our downtime is reduced significantly. That increase in voltage has caused a reduction in string current, which is good. But the increase in voltage has also led to larger AC switching losses in some of the AC components, which is something we weren't aware of when we were planning this out. So this was a lessons learned. And we actually had to introduce more cooling provisions into the cowl. You can see the little, I call them rabbit ears on top of the cowl there. We had to open up our heat exchanger intake to bring in more airflow. So it's very localized heating that we're getting, but it was something that no one was really expecting. So turned out that was something new. And then right now we're actually increasing the, working on increasing the payload to get our second crew member in there, flight test engineer. Currently, we only have been carrying one pilot, mainly due to flight permit limitation, but also up until 1.5, there was actually no room to put a second pilot in, or a second person in, because the BPMU, or battery management unit, pardon me, was taking up that space. Now we have empty space in the co-pilot area, so we're going to put that seat back in. So what's next? Some of you might have heard earlier this year, we started getting interest from potential customers who have signed LOIs for a commercial version of this electric aircraft. You can see with the specs here that we're aiming to meet that it's a much more improved aircraft compared to our prototype. We have extended range, extended payloads, and something else that I haven't really mentioned yet is the noise reduction in the electric aircraft. It's much quieter than the piston. With some, I'll call them point reference measurements, they're not taken in accordance with any rule or regulation, we saw a 20 decibel difference between the baseline aircraft and our electric aircraft, which is a massive reduction in noise. Oh, I'm supposed to say if you're interested, scan the QR code. But why are we doing this? And this is the most important part. So Harbour Air is not new to the concept of urban air mobility or regional air mobility, though I think these terms are getting a lot of attention in the media today, and rightfully so. But we've been serving coastal communities of British Columbia since 1982, for over 40 years. We serve, at our peak, 500,000 passengers per year. All our flights are very low altitude, 1,000 to 2,000 feet. Our average flight time is 23 minutes. Most of our flights are under 30 minutes. It's really nice. If you haven't been out there, I highly recommend you come check us out, go for a flight. We do tours out of Vancouver Harbor. And you'll know that Vancouver is very temperate, right? It's not like Waterloo or Toronto where you get a lot more cold weather and snow. But that's really good for operating with a battery electric airplane. So Harbour Air's approach, though, most importantly, is it's not trying to reinvent the wheel too much. It's introducing a new power plant on a proven airframe. And that lays the groundwork for innovation as well as the certification path. We're not introducing any new architectures or complex software by trying to, make autonomous flight. And we're still aiming to achieve 30% reduction in operating cost on the aircraft and almost 100% reduction in emissions. And I don't know if 100% is truly possible. Ideally it is, but it really depends on where that power is coming from. In BC, we're lucky we have over 90% hydroelectricity. That said, the other companies that are here today, I mean, they're taking other approaches. They have entirely new configurations, novel architectures, and those are needed to fully exploit this battery technology, to take full advantage of its capabilities, to optimize. The Beaver first flew in 1947. It was not optimized for battery electric flight. But Harbour Air's mission is to decarbonize aviation one aircraft type at a time. And I wouldn't be here if I didn't get to work with these exceptional individuals. I work with an amazingly talented team of people across the spectrum of aviation, from power plants to structures to flight test. And I really encourage you, if you're in Vancouver, come for a visit. We'll show you around, show you the eBeaver up close. Thank you very much for having me here today, and I look forward to the panel discussions.
All right, good afternoon, everyone. I'm Zach Taylor. I'm a recent graduate of University of Waterloo, Science and Aviation program. I've worked with WISA as a research assistant. Now I'm working with the Waterloo Wellington Flight Center as a flight instructor. So I was just going to give a quick bit of story time and an intro on what the Pipistrel Velis Electro is like as a student. So 2 years ago, we got our first Velis Electro. I was a student at Waterloo. I wasn't involved with WISA, but I heard we had this electric plane coming, and I thought that was pretty cool. I remember there was one night after a night flight, I wasn't at the original delivery of it, but I'd heard that this cool plane was in the hangar, so I snuck into the maintenance hangar after dark, after my flight, and that is the picture I took of our plane. So that is the first time that I saw our plane. Little did I know that less than a year later, I would get a chance to fly myself. So there's me. My mom wanted me to take a picture of the plane after I got to fly it the first time with our CFI. And it's been a blast. It's nothing scary. I remember not even electric flight, but the first time I ever flew a plane, my mom was like, oh boy, this is going to be interesting. And you should have saw her face when I said, hey, this is the next step. But it flies like a plane, as you'll hear from Paul. It flies like a plane. It's nothing scary. It's a lot of fun. It's a lot lighter than the 52s that I trained on. It's a bit prettier looking. It performs way better, but it's a blast, really. We've done a lot of work with research. First photo on the left there, that is me sitting on the grass at the threshold of runway 32 in Waterloo as the Velis flew overhead. We were doing a bit of research with acoustic testing, comparisons of the Velis flying overhead versus the other training aircraft. And like Blago said, this might not be a car-certified method of training or of measuring noise, but it was a lot quieter, I'll tell you that for sure. And then we did some run-up work as well, some ground testing. There's been a lot, but yeah, it's been great so far. Second photo, that's my buddy Dave and I, research assistants. We were installing a heat plate to block off some cooling on one of the aircraft, trying to keep heat in the battery system, because as you'll hear, batteries don't like temperature variations. So in the winter here, not quite like Vancouver, it gets a little bit colder. So this is one of the ways that we could keep the batteries warm, as well as a preheater to keep the batteries warm so they could charge more efficiently and get us back in the air as soon as possible. And that last photo on the right, last winter, we were lucky to have our second Velis Electro delivered to the airport. And there's it coming out of the container, put together, and yeah, it's pretty quick. So lots of various research projects going on, for sure, as you'll see lots of posters in the hallway, lots of stuff going on in Waterloo. But the biggest, most exciting one for me was this year. We had our inaugural cross-country where we flew from Waterloo to Brantford, where we could recharge and fly back to Waterloo again. Wasn't super far, it's just over 20 miles. Yeah, my parents poked fun at me because I was super excited about my mighty cross country, as they said. But it was a small step, but it was exciting because it's the first time we went somewhere, charged up, and came back. And because we were able to get the charging infrastructure in place at both airports. And as time goes on, as we're able to expand that infrastructure, we'll have more stories just like this, which will be very, very exciting. And yeah, we wouldn't be here without the whole team that brings us everywhere. You can see just a few of us at the bottom right there. That's after we successfully made it to Brantford and had charged up. There's a whole ton of people that get us to where we are. So major thank you for them and all the support that I've gotten so far from them. But yeah, it's been a blast. It's great as a student. It's gonna be great as an instructor, and it's just a whole lot of fun. It's very, very exciting.
Thanks, Zach. Of course, Paul Parker, University of Waterloo. I say it's the students. It's what it's all about for me and my cohort. And of course, what do the students want? That bright future. So thank you, Zach, for helping make it into a reality. Zach said that we have an entire team. That's absolutely right. So I'm going to share some results with you quickly, but it's all of the academics, our flight school partners, Waterloo, Wellington, and others. Then we have our flight instructors, and we have our research assistants, and then there's a whole team beyond that. So this list of names is just to give some of the recognition to the many people that have been helping. And since he's sitting right up in the front corner, I should sort of point in two different directions. Of course, the very first tail was taken, I think, from Bob Connors from Waterloo Wellington Flight Center. Safely took that first tail out of the plane, which was great, that safely under the flight school's wing. But what caught my eye when the first plane was delivered, it was the student who was on site. Gabriel, I'm going to embarrass you because I could see in the glint in his eye, he was not going to leave this plane in a hurry. And guess what? 2 years later, he's still a star on our team. And so just thank you to the flight schools and the students. They're making this all happen. Oh, maybe I should say thank you to our funders and partners as well. They are also an essential part, so I have listed them. Thank you, funders. What that has meant, I love this cautious approach. So it was the crawl, walk, run. So we started with the ground runs. Then we stay within the circuit, just doing the simple circuits. Then you're just going a little further for your upper air exercises. Then you do the pseudo, pretend we fly away to Guelph and come back. And then eventually we do the A to B. So it's a step by step. After you do 100 circuits, you can probably do the 101st. So you have 100 flights this first year. You've got 234 flights on the plane now. So each time it does another cycle, we go, good, that's one more. We just keep adding the experience, and our role as a university is to share the results. I say over 300 flights there because that's including the flights from out west. Sealand has been a great partner with the third pipistrel that you'll be hearing about as well. There we go. So of course we had a plane arrive. Sorry, the graphs are not very bright on this. I'll put the charger in because it's great to have a plane. It's very exciting. But if your charger isn't certified for Canadian operations, you're not going to be charging it very fast. And so it's important to think about the system. And so the airports and the flight schools are just as important as the plane itself. How much flight time? We've got a series of blog posts that you can see by the QR code in the top if you want any of those details. How long can I fly is always a big question. And of course, my academic answer is, it depends. What is your power setting? Higher power setting, you're going to go through it faster. Lower power setting, it'll last longer. Not a big surprise. How many circuits? Well, the SOH, the pilot operating handbook rather, says about 10% per circuit. So if I go from 100% down to a 30% reserve, that would say 7 circuits max. What did we find when they tried year 1? 7 circuits max. So it's sort of a, oh wait, I have the most boring report to tell you. You have green for safe operations, orange for caution, red for reach the danger zone. This is all green. Sorry, it's not just because I'm an environmental prof. It's nice to see temperatures are green, operations are green. Green is a good color for this exercise, and that's what we've been finding. Wait a minute, you said it might not like the cold temperatures? Sorry, I said I love our students. The RAs are great. They go out and they charge the plane, get it ready. But what happens when the temperature drops? Last November, we said, yeah, go out and charge that plane. Yeah, it's that usual 1 hour charge, you see, so starting in sort of May, June, July, August coming along. November comes along, student goes to charge the plane. It's hour 1, hour 2, hour 3, hour 4. Hour 5, 6 hours to charge this plane. What operation is going to wait 6 hours before you get back in the air? Obviously the students wanted a solution. Thank you, Pipistrel. They have a solution. You have a battery preheater, and you just saw the plate being installed. So again, we identify challenges and try to help find solutions. So solutions are being found. There are challenges ahead. And in our second year, we go, wait a minute, now that the battery has aged, it's 20% lower on the state of health. Does that mean it's going to be different flying this year? And the POH again says you'll probably lose one circuit. And guess what our experience was? That's right. 6 circuits is the most instead of 7. So again, just following the check marks, verifying what was happening. You're interested in how much money am I going to earn on this plane? How many hours are we going to fly in the day? And so we said, okay, let's let some students fly the plane, see how many hours we get. This is comparing a good week of operation to a not so good week of operation. In the good week, we were running just about on a 2-hour cycle. We actually averaged 2 hours and 2 minutes. So very close to sort of 50 minutes flight time, 54 minutes charging, and another 15 minutes for checks and briefing, etc. So roughly a 2-hour cycle it was going through. And that meant, starting at 8:30 in the morning, well, yeah, you could get up to 6 hours. Over the week, it averaged a bit over 4 hours flight time. So that's what a flight school could expect to be charging 4 hours per day on a good week. Of course, there were days and other weeks when it was rainy and the staff weren't there and so on. So you're getting 2 hours a day. And Bob doesn't want to hear about those days because you're only getting half the revenue amount. But anyway, it gives an idea of what we're finding in these conditions. And of course, being from the Faculty of Environment, I had to say, yeah, well, one of the big goals was carbon reduction. What do we actually achieve? And of course, we love hearing the zero carbon that people talk about. Well, there are 0 emissions during flight, that's right. But sorry, we just like our harbor air friends, we have to recognize even that hydropower does have carbon embedded in it if we look at the life cycle. And so the coefficients have been revised for the last year. So the BC Hydro, you're recognizing the carbon involved in building the dams as well. So if you look at the life cycle, it's not a 0 source. And so looking at that, we took the 172 as our reference for how much carbon emissions you have with your life cycle of the fuel versus the life cycle of the electricity. And yes, it actually delivered a 99% reduction if you have a low carbon source of electricity like in BC. But the good news is, even if you have a not so low carbon fuel, like if you're using Alberta electricity, which is much more natural gas based, it was still a 90% reduction. So dramatic improvements there. And again, we just keep asking new questions, collecting more data, and one day we hope we'll get to a certification stage. Thank you very much.
Hi, everybody. I don't have a fancy presentation like everybody else had, so it's just me. My name is Madison Fergala. I'm a sales representative with Apex Aircraft Sales, and we are the Canadian distributor for Pipistrel Aircraft. So you've already heard a little bit about the airplane. You've probably seen it around. Its today's focus quite a bit on it. But I'm going to talk a little bit about the history of Pipistrel and how it came to be and what we're trying to do to advance it in Canada. So Pipistrel Aircraft is actually, the name Pipistrel comes from a derivative of the Latin word for bat. And this company was founded in Slovenia. And at the time in Slovenia, hang gliding was actually prohibited. And so these people would take their hang gliders up to the cliffs and they would jump off at dusk, hoping that if anybody looked up and saw them, they would just think it's a bat. And so that is how Pipistrel got founded. And so over the past couple decades, they've gone from hang gliders into gliders, creating the first electric self-propelling glider in the world, and then into certified aircraft, creating the Velis Electro, the first EASA certified electric aircraft in the world. In 2021, Textron Aviation, who owns Cessna, Beechcraft, and Bell helicopters, purchased Pipistrel for $250 million. It wasn't just for the electric airplane. Pipistrel has quite a depth of knowledge in battery technology, certified aircraft, and RPAS, so remote piloted operations. And so the intention there is to grow each one of those within the family and have the Textron money essentially behind that growth. It is a Slovenian-based company and will still continue to be a Slovenian-based company though, compared to the other Textron companies that are American-based. So how does that work in terms of coming to Canada, and where do we see that going? So, as you've seen, Waterloo Wellington was the first to buy the Velis Electro in Canada 2 years ago. And since then, we've sold Waterloo Wellington one more, as well as a company on the West Coast called Sealand Aviation. So that is really the starting point for commercial operation of this aircraft in Canada. Earlier this year, Sealand Aviation was granted an exemption, so the first in Canada to be able to teach ab initio training on an electric aircraft. I will say the airspace for Sealand is a little different than Waterloo Wellington. They're a small airport. They don't have the same, their practice area is not 15 minutes away. So what that allows them to do is more than circuits. It allows them to teach upper air work in this aircraft without having the restrictions of using 15 minutes to get to a practice area. So what's coming next for Pipistrel? We are looking at, everybody wants to know about the battery. When do we get longer lifeline? When do we get more time in the aircraft? We're probably 3 to 5 years away from a longer battery. What's coming next for us is better charging systems. So faster charging, allowing for less time on the ground. As Paul mentioned, it is approximately an hour of flight for an hour of charge. So in a flight school business day, that really does limit if the aircraft has to be on the ground for an hour. So the next steps would be the hope that faster charging would allow for a 30-minute turnover time, which is just enough time to, park it, brief, do a walk around, and then you're back up and going. The next step would also be, and Paul mentioned it, and I think everybody here on this panel has mentioned the charging infrastructure. It is, of course, just like Tesla and electric cars in the beginning, the charging infrastructure is at the very beginning, and we will need to see that increase. So the hope for Pipistrel is to have CCS2 adapters. And so for anybody who's not, an engineer and doesn't know what that means, that essentially means you'd be able to charge your airplane with the same charging system for electric cars that are already in the facilities at airports. So if you've got electric car stations, charging stations in your airport parking lot, you should be able to then charge your electric aircraft on the apron. That is what's sort of coming next in the advancements from the technology for Pipistrel. And actually, the hope also as well in Canada is that early next year, we will see the Pipistrel Velis Electro fully certified and able to use for commercial operations within Canada. And that's my spiel.
So hi, I'm Bob from Waterloo. We have been very fortunate to be the flight partner with the university. We've been the flight partner in a flying training program since 2007, and since the advent of WISA and some funding that came through a variety of sources, that's resulted in a number of things, including the Pipistrel aircraft and what Zach and Madison have talked about already. We've been around for a long time. We're 92 years old, started out as a flying club, and over the years have morphed into one of the largest flight training educational organizations in Canada. And we like to be close to the head of the pack. So we're very interested in things that are new, different, evolving, future-looking, and certainly the electric aircraft. When Suzanne said, "Hey, Paul has this idea about an electric airplane. What do you think?" Sure, bring it over. We didn't know what we were getting into, but we proved we were the test bed for seeing what kind of challenges we were going to face. So the first was charging, and there's the technical stuff about the type of the charger that Pipistrel provided, but more so it was what the hydro authorities in Ontario wanted compared to what the European authorities designed to. So we don't have 400 volt power in Ontario. So in order to plug in the 400 volt charger, we had to transform 600 volt power down to run a whole bunch of wires and cables and blah, blah, blah. So what seems like, sure, plug in the charger seemed like a really easy thing to do. It took 4 months. And then when the BC organization got theirs, same charger, BC Hydro wanted different requirements to hook it up and wire it into their system. So there are some regulatory challenges that are beyond transport. So we've flown about 100 hours on the first Velis, and a variety of testing with both range and endurance, the kind of stuff that Paul's already talked about. But we've also done some testing of the flight training exercises in the electric plane to see how that compares and whether you can achieve the same outcomes in approximately the same time. So we've had a number of instructors work as test pilots, if you will. We haven't actually trained anybody real, so the people that are the trainees are not getting time for the time that they spend in the aircraft yet. That's coming. I expect that we'll see that early in 25 by way of the exemption that Sealand was the first to get. So then we'll be able to actually train real people for time that will count in their logbook towards PPL. So that's kind of next step in terms of usefulness. Part of a suite of activity with the university was a sim center as well. And again, so funding offered us the opportunity to have use of 3 airline type FTDs, a 737 MAX, a A320, and a Q400. And our part of the deal was to build a space to house that. So that was done. And we built the building in as near a green kind of fashion as we could, including solar panels to supplement hydro grid consumption. So, and just a couple of days ago, we got word that the local hydro authority has approved net metering. So it means we'll be able to hook it up and feed excess hydro that is not being used in the building back into the grid on the airport. So that was a major step. It took several months, 3 hydro authorities, the airport, the region, all getting involved in what will this do and how will it benefit and that sort of thing. But I hope that early in the new year we'll actually have that connected and be able to see how much the solar system that we put on the building will reduce the hydro consumption in the building. Aircraft certification of the Velis, we have pretty good working relationship from a flight training and regulatory point of view with Transport Canada, both locally and in Ottawa. And so they got very excited when the first Velis came. Have been to Ottawa folks have been to visit the Velis and test it and that sort of thing at our facility a couple of times. And they are working on interim regulations that are by way of an exemption, and they are working on full certification regulations that'll probably end up looking like a hybrid of the European CSLSA and the American kind of LSA standards. So we're optimistic, and they're supposed to be doing some testing in Slovenia at the factory of other Velis aircraft, and we hope that sometime in 25 we'll see certification. I think, Madison, you said spring? Yep. Okay. So that's part of the quiet work. It doesn't show anywhere, but we've been working using the flight data that we've had, the instructor and student experience that we've had to help TC to get their minds around how this is the same or different from a gas-powered training aircraft. The second step is once it's certified, we have the authority to use it in flight training. Right now, that's been given to Sealand on an exemption basis, but once it's certified, then we would expect that it will be certified for certain exercises. You can't spin the aircraft, so it's not going to do everything, and it is day VFR only. So it will have some limitations. You won't be able to do all of the training, but you'll be able to do probably 60 to 70% of a PPL syllabus. We also learned a lot about maintenance. We've had a couple of people from Sealand, a couple of people from our place, a couple of people from Brantford attend different Sealand maintenance training courses, And most of that maintenance is understanding the battery system, the charging system, and the cooling system. One of the things that hasn't been talked about is the Velis Electro has a liquid. It uses essentially antifreeze to cool the batteries. So that is a little bit of a different scheme in an attempt to regulate the temperature range within the aircraft. Other than that, maintenance is maintenance. It's quite a bit simpler than many things. The wings pop off in probably half an hour, and maybe pop back on in an hour and a half. But there's really no surprises there. So the questions that we need to look at, range, battery endurance is number one. If we had a battery that was good for 2 hours, in our environment, that means you could do a cross country from Kitchener to London, St. Thomas, Brantford, and back, and still maintain a 30% reserve in your battery, based on the experience so far. So having double the battery capacity is a huge wish list. Client acceptance, so far the students, Zach and his counterparts have gotten a real kick out of it, have been avid advocates for the aircraft. So it'll be interesting to see as we roll it out initially for scenic flights and electric experiences to the broader community, what kind of acceptance we get. Noise, for sure, much less. It's noisy on the ground, but when it flies overhead, it's considerably quieter. And the airport, YKF has a noise monitoring setup that we've used a little bit to try and test that. We don't have fully quantifiable data on that, but there's no doubt that it's quieter. So battery replacement cost, that's an open question. How long will it be in flight hours before you have to replace the batteries because their state of health has degraded? And what will that cost? In the Velis, there's 2 batteries, fore and aft. So that's an unknown. We'll have to see. And in terms of operating costs and business viability, that's an open question. And then durability in flight training. Students sometimes are not gentle with airplanes. Sometimes, occasionally. So we've had some hangar rash and various and sundry mishaps with the aircraft, and we'll see how we have to handle the aircraft on the ground so that is reduced and doesn't take it out of service for periods of time. In the long run, I'm interested in eVTOL. I think that's the future for pilot training in terms of a new kind of pilot and pilot training, and look forward to Beta's work and Bai in the States and a few others to see what that next step looks like. So we're keen to keep working with the university and hopefully be leaders in Canadian electric aviation. Thanks.
Yeah, thank you very much. I really want to thank our panelists for the great topics they chose and the great conversation we created here. We have some questions, but I don't know. Should I start? I'm looking at the app. There is no questions coming up here. If you have any questions, please send them out on the app that we have on this session. And if there is no questions from the audience, I start with one question myself. So we talked about the building of electric planes and all the challenges that comes with it. And I think we are just starting the whole process right now. So I'm not sure how far away from replacing the whole fleet to getting to regional flights, for example. But the broader question I have is, how do you see Canadian ecosystem for accepting the electric planes for regional flights, and what type of changes you see that might be coming in our infrastructural changes and so on? And the major question is who has to pay for all these changes? If we have infrastructural changes, who is going to pay for this? Is that Beta? Is that the airline? Is this the flight schools? Or how should we accommodate all these upcoming changes to make sure they are actually happening?
Yeah, great question. There's several points there. I'll try to remember and address as many as I can before I hand the mic to someone else. We've been flying piloted test flights for almost 5 years now at Beta. So there are changes that need to take place, but there's also a tremendous amount of infrastructure and existing pieces that work really well with these platforms. Again, one of our 2 aircraft that we're certifying is a CTOL aircraft, again, runway dependent, and the other is runway independent. Someone, and I can't remember who it was that mentioned it, there's a tremendous amount of service that's not available to communities, whether that's passenger service, medical supplies and needs, EMS service, or cargo and logistics, and those aspects. So that's really where we see this entry point, certainly in the US and also in Canada, is connecting those communities, again, whether it be logistics or cargo, passenger operations or otherwise. So that's part of the reason we're taking the approach we are, launching a certified Part 23 CTOL aircraft, again, to utilize existing infrastructure, and then moving into our VTOL aircraft after that. So we're a cargo first, medical, and then passenger. And again, we see that from an acceptance standpoint and a proving ground standpoint, really as a path that we think is going to work, again, on both sides of the border. Thank you.
So with the almost. Okay.
It was bound to happen.
So with the CAE program, we'll be operating our aircraft primarily in the United States. So we have our own challenges there. But just from a Canadian point of view, one thing I see is a few little hubs are starting to build up in Canada. And I mentioned Saint-Hubert a couple of times. It's no coincidence that we're going to be operating out of Saint-Hubert. Service Centre Canada already are working with Pratt & Whitney on their hybrid demonstrator program, and they have already some infrastructure awareness at the airport, for example, crash crews, how to deal with electric or batteries on aircraft, etc. So I think we're gradually going to see little hubs showing up throughout the country that can actually accommodate this. We're an A2A aircraft, we're not going very far. When the circuit works, that works just fine for us. But that's the way I see it, it's going. It's going to be little hubs and then spreading, and I think Saint-Hubert will be one.
And I'll just build upon the last point there for them. Who's going to be paying for this infrastructure? Because this is a common theme that we're seeing specifically among our existing flight centers, our regional and under and remote airports, and some of our international airports. And we've been spending a lot of time building up that awareness with our utilities across the country, so that as airports see themselves as becoming energy hubs of the future for both aviation uses, ground transportation uses, and additional new infrastructures as well. How is that business model of both, yes, flight training today, new energy provisions in the future, and then what that could mean for maybe a real estate play around those airports as well? There are different revenue models that need to be incorporated from day one, because if not, the airports, the flight schools, or the OEMs are not going to be shelling out the hundreds of millions for these new advanced technologies. So we're putting a lot of effort in how are those revenues shared initially from day one, so it's not a capital expense that puts the entire economic chain at a loss from day one. And just expressing on the challenges of existing aviation policies for the way our airports are funded, and of course our flight schools as well.
I mean, for Harbour Air, as I mentioned, the flights are perfectly aligned with the capabilities of electric aircraft today. It really depends on your mission. The potential customers have shown interest in the electric Beaver are connecting communities. They're skydiving. It's a short mission, 15 minutes, in a place where the government has basically threatened to eliminate their sport if they don't clean it up. So there's unique situations where there's opportunity, and we have to, I think Canada is a good opportunity, or there's a lot of good opportunities for Canadian companies or Canadian partners with our American partners to take advantage of those opportunities. So we need to make sure that we don't look at it too high up and say, oh, this won't work across the ecosystem. No, it's going to work in very niche points to start, just like every new technology. At the airports, you can have electric vehicles towing airplanes. You can have electric vehicles delivering baggage. You can have, like, it's not just the airplanes that are going to be electric. It's going to be every vehicle is going to need some power, and it's going to have to be electric. So it's going to have to be everyone who's at the airport utilizing that infrastructure that's going to have to help contribute to it. So I don't think it's, we can't just say, oh, it's up to the electric aircraft manufacturer to build that infrastructure out.
Okay, so maybe I'll go over some of the questions that I have. There is one question for CAE, Richard. So the question is, why did you choose the Archer as the base for the electric powertrain as opposed to a newer aircraft? Are you planning to sell the technology as a retrofit kit in the future, or just use it in the house?
Okay, so we're basically taking the one step at a time point of view. We've got lots of Typer Archers, so that's basically the fundamental reason why we're converting the Archer. We also knew that we could get HIPOS support with the program. They weren't doing one independently, we do independent ones, but they're not doing it themselves. And yes, if we succeed, there's a market for this type of aircraft. So we know that's in the future, but right now we're concentrating, first of all, get the prototype in the air, and secondly, make it suitable for our own training organization in Arizona, and then we'll see where it goes from there. So these are all known things, but as a company, converting what we have into something that's more sustainable and environmentally friendly is our first focus.
There is another question here regarding the temperature of the battery, temperature control. Electro needs to keep the battery warm, Beaver needs to cool it down. And will there ever be an application for northern ops? And is there stuff in the works to better insulate the batteries? Maybe those of you who are in the manufacturing or selling the batteries and stuff.
So the battery system we have on 1.5 actually has provisions built into the battery modules to cool batteries down. But those provisions aren't in use during flight. You don't need to carry the extra cooling weight while you're flying. You can make use of that payload for passengers or baggage, cargo, whatever. And then on the ground, you use the cooling system, and I won't call it a cooling system. I'll call it it's a conditioning system. So it's not necessarily cooling; it could also be heating, depending where it's being used. The nice thing about batteries, I'd say, from our experience, like we've flown in sub-zero temps, and the nice thing is that the batteries tend to take care of themselves for heating. So usually for us, we need to cool them down. However, I think your situation was specifically during charging. You had the issue. So maybe you can talk about that.
Yeah, so we discovered that, you know, small plane, I guess it makes less heat with the batteries, but in flight there's a lot of cooling. It's also liquid cooled. So cooling, we actually had no issues with that at all. When it came to the winter with the sub-zero temperatures, we found that as you come into land, you bring the power back, you basically land power off, and then you taxi in all low power situations, and plus a whole lot of cooling on the battery. By the time you shut down, the battery's nice and cold. You go to plug it in, and the charger with the battery management system can't efficiently charge the battery because it's kind of shock it if I'm correct like that. Good signal.
Thanks, that was the experience doing it, and thank you, Gabriel, for actually charting what the curve looks like. It's the battery management system that controls the temperature and the charge rate. I would add, this is really generation 2 from Pipistrel. That the Alpha was designed with an air-cooled battery, they found the temperature variations, and they decided that they would get longer life component parts by going with the liquid cooled system to be able to manage temperatures better. So it's sort of a corporate decision of which way you're going. And of course, it was designed for cooling initially, but oh yeah, Canada, we also wanted it to be able to be heating. And guess what? The same system will let you do both. So the preheater has been added.
Yeah, just to add a small part onto what Paul was saying. So the generation one of the Velis Electra did not come with a battery preheater or cowling covers essentially to block the air from getting into the aircraft during flight. And that has been amended. So any of the aircraft that were purchased before this was created were retrofitted, like your first one, and now it is standard on all of the Electras. So that issue has been kind of put to rest.
The other temperature issue is cabin heating. It's cold in the wintertime, and it doesn't have to be real cold for your breath to make you IFR in no time. So they found some workarounds in Europe, but unfortunately, the windshield clearing thing, TC didn't like it, so we still have some work to do there.
Yeah, airflow inside the cabin, I think, is our bigger concern compared to airflow for the battery.
I actually did get an email from an operator in Nunavut a couple weeks ago expressing support for the program, expressing interest for an electric airplane when we have one that can fly up there. I looked at his mission and it was definitely beyond our capabilities right now, but I think it's encouraging that there's interest. Someone wants to fly an electric airplane in the coldest place on Earth.
I can say there's probably hope for batteries in hot, cold temperatures because it's relatively easy from an engineering perspective to control the temperature of the batteries, and it's all about the battery, the cell temperature. The ambient temperature, it's just your starting point. You've got to cool down or heat up to get to the good zone for the batteries to charge or operate, but once you're there, it's a relatively straightforward task to manage it. So it's all about the temperature, managing the temperature of the cells. You can overcome the ambient conditions.
So there are some questions on hybrid electric propulsion in Canadian aviation. So what do you think? What do you think about the future of those systems? And do you think there is any capacity to make the aircraft hybridization with other devices like fuel cells? So two questions: combination with fuel cells and also hybrid.
Hybrid may be over the horizon for us, is it? So I'd like to start.
So one of the big things with hybrid is we look at the different steps, and Paul, I'm going to use your language on that crawl, walk, run side. There needs to be different technology advancements on route to that ultimate goal of getting to net zero. Hybrid is one of those stepping stones that is being researched. I know the National Research Council spoke about their program that they've been doing on their hybrid electric aircraft. These are going to be unlocking technologies that will further help our electric side, further help our fuel cell side, and be an important next step on route to that ultimate goal. Is that the all solution that's going to be what's going to be operating in Canada? Not necessarily, but it's how do we take those learnings amongst the ecosystem that can further help additional developments on route to those operations. So that's where we're supportive of the hybrid side, but not necessarily as an end state solution.
Any comments? Or?
I think there's a really good potential to help with the establishing the certification path for some of the components, especially the batteries. This is quite possibly the biggest challenge or hurdle we have to overcome is actually just deciding what are the rules going to be for certifying these batteries, because the regulators are not 100% certain yet. And we're participating in discussions with regulators. I think every manufacturer here is also probably participating in those discussions. There's many working groups going on at ASTM. So we're a shameless plug, and I have no real affiliation or benefit from ASTM other than I participate in it. I highly recommend young professionals in the audience to check out ASTM, start learning about the aircraft standards, because if you're going to be working in general aviation, you're going to need to get familiar with those standards. And that it's all free for the most part to attend and participate. You learn and get access to some of the smartest individuals I've met in my career so far.
Okay, I think this question is for Sai. How do you see eVTOLs complementing or replacing existing urban transport modes over the next decade?
Yeah, I should absolutely think it's a complementary role ultimately for eVTOLs. Not a replacement by any means, but really allowing those operators to expand their network and really find new markets ultimately and unlock that middle mile or last mile, first mile, if you will, that has been given over to other modes essentially. So whether it's passenger, again, as I mentioned, cargo, logistics, or medical, where another mode would normally take that place in those certain situations, maybe that operator now can unlock that with the solution. So that's really what we're focused on learning. We're working with our partners and again, others in the space to really understand what those applications are. It's not just something that we're building a product and handing off to our customers and saying best of luck. It's again really understanding what we need to build out that ecosystem, as I mentioned, to really make this a reality. So that's our focus.
Thank you. I think the next question would be for Richard and University. So that's the question on keeping, the weight of the battery. How did you manage the weight of the batteries? How long range we need more? And it might be because they are heavy actually. I don't remember what was the weight of the battery, but it was a heavy one.
So the example I gave earlier was the fuel system full of fuel on a Piper Archer is about 150 kilos. That was to give you the over 4 hours of flight duration. The equivalent mass is 150 kilos of battery is going to get you 20 minutes. 20 minutes is utterly useless. No one's going anywhere with 20 minutes, not even off the ground if they need the FR reserves to go with it, because that's 30 minutes. So you just have to basically keep multiplying the number of batteries that you put on the airplane within the max takeoff weight that you have. And we're lucky because we've got a fairly high max takeoff weight, and you can take quite a lot of batteries, and it can get it up to the hour plus that we're looking for in terms of flight times. So we can do it just by adding batteries where previously there was a fuel system, 2 passengers, etc., etc. So if you stay within the max takeoff weight, we're only two crew now, where we used to be 4 occupants. So that's where the battery capacities come from. But it's still only giving us an hour.
Did you have to do anything with wings? Did you have to do anything with wing structure?
Well, that's where we've been fortunate, because with the Archer having the fuel tanks in the wing, we've basically been able to replace, as long as we had the volume. So there's been a little bit of a change just to take in batteries where there was previously a fuel tank, but the mass and the placements of the mass is around about the same. So that's very useful. And that was one of the things that I said earlier is, if anything broke, don't fix it. Let's keep the weight in the same place. It makes loads and things like considering spin and such like with the inertias of these systems. It keeps it very similar to the baseline aircraft. It makes it a lot easier to come up with the rationale for certification. So don't touch it, keep the mass where it was, and that's basically what we've done.
Yeah, we see obviously 2 components. Obviously, there's the energy density of the batteries being a major component, but then also the containment of those batteries in regards to making sure that's a safe and closed system. So we are really pleased with the energy density with the batteries that we have on hand today. And we see it, again, as a real opportunity to unlock multiple missions for our customers. But where that goes in the future, you can either extend the range or increase payload, or both, as that continues to evolve. So we feel like the platform will just continue to be more and more capable as that runway continues. So we're really excited about what there's today and also for the future of that.
I agree with what Scott said.
Okay, so the last question would be all related to myself, because I'm coming from academia, and we've done lots of research on e-plane integration into our regional fleet, and we see a lot of potentials in Canada, for example. We've been able to optimize the locations for electrifications of the airports, and also we've done lots of studies on the data that generated by Paul and Waterloo Flight Center to see what would be the optimal power setting for the e-plane, for example, when you're taking off and you're cruising, when you're landing, and so on. But my main question here is, how do you see the role of academia? how do you want to be more involved? I know, Bob, you're already very well involved with academia. But what are the things that we can do? We have lots of expertise in chemical engineering and building batteries, for example, designing batteries, optimizing data analytics, mechanical engineering, and so on. Where do you see our role in your production or research?
I think it's a great question. I'll be really brief to allow others to comment on it as well. Workforce development, I think, is a major component. We're very focused in that aspect. So just providing that pathway for the students and the participants in the space really to enter into those segments that they might not even be aware of right now. So we're very active in that space. And we hope that's part of the focus.
Two things. One, more hands-on project work, less exams. Two, and I mean like really good project work, like build, test, fail, build, test, fail. And then second is awareness. I think it was highlighted in the keynote this morning. A lot of people, myself included, did not know that this job exists when I was in university, which was not that long ago, if you can tell. And I think that awareness is key to getting our workforce developed back to where it needs to be. And that's all I have to say about that.
I was obviously in the academic year before I got just there's one specific topic that I think is a real pain in the neck for electric aircraft is the topic of reserves, and to come up with a real good bulletproof set of research that allows the likes of the Gamma white paper that came out where reserves become more performance or safety based rather than prescriptive. I think that's where extending the range and duration of these flights is going to come from. Because being stuck with what we have at the moment for missions that are half the length of the reserves doesn't make sense, but there's no bulletproof case out there today that justifies to go to the authorities to make that so.
And all this includes to build upon the human workforce capital. We have incredible organizations already here that need great human beings working at them. So please connect with the organizations here as their future workforce. And just a kind reminder that there's the technical needs, but the incredible amount of support services for the entire aviation industry to thrive. That's back office, front office, flight attendants, and our pilots and air traffic controllers. So know that those jobs are out there and will continue to be demanded as the aerospace industry expands in our country.
I have a reserve question. The transport has just looked away for us for right now, and not because we haven't told them, but they know that we can't meet a 30-minute. You barely take off with 30 minutes time. So they've been understanding of that, and I guess if we start to do longer flights, then that may become more of an issue. But as you say, how fast does the battery degrade? Does it degrade like the gas gauge in your car? The last quarter tank is gone in minutes. And once we have reliable data to support that, there'll be a new standard.
So the Pipistrel case with the 30% SOC reserves is enough for 2 circuits. And for an A2A type aircraft, that makes perfect sense, but how do we make it so?
Sorry, I just want to touch on what Bago was saying about the workforce and what's needed. And so in Canada, we hosted about a dozen engineers to come out and learn how to maintain the Pipistrel aircraft. And so they were able to take the entire aircraft apart, powering forward, and put it all back together in a span of 5 days and run it up with their issues. And so I do think that that's going to be something we're going to need to see coming out of this is the engineers. We're going to have to teach engineers who are already out there and licensed how to maintain these aircraft. But if schools can start teaching it at that level, so that new engineers are coming out of school with an understanding that this is where the industry is going, I think that can be a really big help instead of having to teach them after they graduate.
Wonderful. So on behalf of Merdad, my co-chair, and all of the folks at WISA for hosting the Sustainable Aeronautics and our panelists, we want to say thank you for listening to our conversation this afternoon and appreciate the conversation to continue thereafter. So a hand for all of our panelists, please.